Yeah,
Okay.
you can go ahead with your introductions. It's almost 5 after, so we should, more people will still continue to filter in, but that's fine.
Okay.
Thank you for doing that introduction, Atsuo.
Okay. Good morning, good afternoon, and good evening. Thank you for joining our meeting for May. Today's speaker is Shige Karino from the Kyushu Sangyo University, Japan. And he has been working for accretion processes around neutron stars. And also he has worked on the seismology of neutron stars. And recently, he has been working on the evolution of binary systems with neutron star. And today, he'll talk about the BE-type high-mass X-ray binaries as progenitors of ultraluminous X-ray sources. So, Shige, please start when you are ready.
Okay, thank you very much. Okay, let me share the display. And oops. Okay. Okay, hello everyone. First of all, thank you very much for organizers and audience to give me such a good occasion to talk in such an international environment. Because of COVID-19, we don't have enough chance to talk in such an occasion, so it's very good chance for me to introduce myself. Okay, before starting my presentation, I'm afraid that most of you do not know me, so please let me introduce myself briefly. Well, my name is Shige Karino. Well, originally I have studied about neutron star oscillations and resultant gravitational waves when I was a student. But after getting the degree, I have moved to Italy, Sissa in Trieste, and I have started studying about the accretion processes onto magnetized neutron stars. And then I have moved to Malaysia and I have studied about high mass X-ray binaries. And 10 years ago, I have come back to Japan and now I'm studying about binary evolutions and corresponding accretion processes. So in today's presentation, the main target is about ULXs with neutron star radiation sources. Well, as you know, ULX is a point-like object that shows X-ray luminosity above the Eddington luminosity of stellar mass object. And that is not in the central core of the galaxy. Well, this is the X-ray image of star-forming galaxies, and these bright point sources are all ULXs. Well, originally, the sources of ULX emission was thought to be black holes, but it is unknown whether the black hole is stellar mass black holes or well, accreting massive black holes. If the sources of ULX emission is an intermediate mass black hole, this is very important for the formation scenario of supermassive black holes in the galactic center. Well, it is shown in famous Lees diagram. There are two scenarios for the formation of supermassive black holes in galactic center. A direct collapse scenario in which a massive cloud collapses directly into supermassive black hole in this way. And a bottom-up scenario in which smaller black holes merges to construct a supermassive black hole, like this path. Well, the existence of intermediate mass black holes in the process of giant black hole formation supports the bottom-up scenario strongly. So it is very important whether actually the intermediate mass black hole exists or not. However, a surprising report has been published in several years ago. This one. The source of a certain ULX emission was revealed to be a neutron star, not a black hole. Well, the target of this previous work is about ULX named ULXM82X2. Well, this source is the second brightest ULX in the star-forming galaxy M82, and a clear pulsations in the right curve was found in the X-rays from these sources, like this. This is a pulsation. And this finding strongly suggests that the source is a rotating magnetized neutron star, not a black hole. A detailed analysis was immediately performed, and the orbital elements of the binary systems were estimated about this object. As a result, it was found that the donor providing mass to the neutron star in this system is massive star, which mass is probably larger than 5 solar masses. That is, this ULX system was found to be a high mass X-ray binary powered by neutron star. Once a ULX powered by a neutron star has been found, the previous observational data have been analyzed in detail. Then, more and more ULXs powered by neutron stars are found, and at present, about 10 systems, 10 ULXs are thought to be powered by neutron stars. Well, this is a list of relatively well-known ULX systems, and some of these objects show transient nature, so it is suspected that the behavior is just the same with the B-type high mass X-ray binaries. Well, there is also in this list there is one object found in our galaxy that exceeds the Eddington luminosity of a neutron star, and about this object, by the optical follow-up observations, it is found that this object is confirmed to have a B-type donor. So this object is actually high mass X-ray binary with B-type donor. And the objects in the last list were ULXs that show X-ray pulsations. However, it is known that some of the non-pulsating ULXs are also powered by neutron stars. For example, the object known as M51 ULX8, this object does not show X-ray pulses. However, a cyclotron resonance scattering feature is seen in its spectrum. So this suggests that the central object of this source has a strong magnetic field. Therefore, this object is considered to be powered by a neutron star also. If there are many such objects, a large proportion of ULXs without pulsation may in fact have neutron star central object. So such kind of neutron star powered ULX is the number of such kind of objects are gradually increasing. So it has been several years since the discovery of ULXs radiating from neutron stars. But there are still many points about these objects that are not well understood. Here, from now on, I briefly would like to give an introduction to some important issues about neutron star ULXs. First of all, there is a lot of discussions about the strength of the magnetic field of central neutron stars in ULXs. At first, neutron stars that would become ULXs were expected to have a strong magnetic field. The reason is that in a strong magnetic field above the quantum limit, the X-ray scattering cross-section becomes significantly smaller, so strong radiation can be obtained. And for the prototypical source M82X2, under the assumption of rotational equilibrium condition, also it is suggested a relatively strong magnetic field. And the magnetic field of the rotating neutron star can be estimated as like this. And the mass accretion rate can be obtained from the X-ray luminosity, and by using typical values of neutron stars, the magnetic field strength of this object becomes in order of 10 to 13 Gauss. It is very strong as a neutron star magnetic field. However, recently it has been suggested that most of the neutron stars in ULXs have not reached rotational equilibrium. In fact, it is said that the magnetic field of a neutron star does not necessarily have to be strong if the magnetic field is estimated by different methods. There are several methods to estimate the magnetic field of the neutron star is suggested. And recent studies argued that it seems that neutron stars in ULXs are not so different from normal neutron stars in high mass X-ray binaries. That is, most of neutron stars in ULXs have magnetic field strengths in order of 10 to 12 Gausses. And also, how matter can accrete to the neutron star is also an important problem. This is because X-rays above the Eddington luminosity are emitted, and the accretion material is blown away by this strong radiation pressure. Many numerical calculations have been done on this problem. And also, theory suggests that accreted matter should be captured by the neutron star magnetic field before the mass loss becomes too large is important. As accretion matter are blown away from the accretion disk inside the radius at which radiation pressure becomes dominant. And this radius is called spherization radius. Hence, the magnetic radius, that is the radius where the magnetic field of the neutron star, magnetic pressure of the neutron star magnetic field becomes dominant. The magnetic radius should be quite near to the spherization radius is important to reduce the outflow rate of the accreting materials, and to get enough large accretion rate, such kind of similarity of these two radii is very important, it is suggested. And also, beaming is another interesting problem. If the direction of the radiation is concentrated to the magnetic pole region, the actual mass accretion rate can be much lower. However, analysis of the pulse profiles shows that beaming is not very strong in neutron star ULXs. This implies that a large mass accretion rate is actually achieved in these neutron star ULXs. And finally, it is also an important question. What fraction of ULXs are of neutron star origin? This, well, in turn, this also means that the proportion of black holes in ULXs should be determined. The study of neutron star black hole ratio in the universe is also important from the point of view of understanding the mechanism of supernovae. Of course, the number of intermediate mass black holes is also key to the problem of supermassive black hole formation. Because of the its brightness, ULXs can be observed even in far galaxies. So they are very useful systems in determination the neutron star black hole ratio in various environments, for example, low metal environment and so on. However, the available information is very limited, so it is important to establish a method or theory to determine the neutron star sources in among all ULXs. The methods to select neutron star ULXs from the spectral features are being actively debated. In order to get a hint on how to obtain the fraction of neutron star ULXs among the all ULXs, in this study, we will examine the relationship between traditional high mass X-ray binaries and neutron star ULXs. So, from now on, I'd like to introduce my recent studies about this problem. Well, traditionally, high mass X-ray binaries have been classified into two types, supergiant type and BE type, depending on the type of donors. And it is well known that these two types of high mass X-ray binaries occupy different regions on the Corbett diagram. Corbett diagram is the diagram right here. This diagram shows the relationship between the orbital period of the high mass X-ray binaries and spin period of the neutron stars. And when we plot high mass X-ray binaries in these diagrams, the B type shown by open circles occupies the different region from the SG type high mass X-ray binaries shown by field symbols. That is, supergiant type with a supergiant donor occupies the upper left regions, and the accretion mechanism of this supergiant systems is loss lobe overflow, mainly when the orbital period is shorter than several days. On the other hand, those systems, supergiant systems with orbital period of more than several days, are considered to be fed by stellar wind accretion. And both supergiant types shows persistent behavior. These systems shows persistent behavior. On the other hand, the B-type high mass X-ray binary systems occupies the lower right region, like this. And this object shows transient nature. So these two types are somehow different. Okay. And as mentioned earlier, some of the neutron star ULXs show transient nature as like B-type high mass-accretion binaries. And also, some of neutron star ULX systems are also known to have B-type donors. And they are located in the same region as B-type high mass-accretion binaries on this Corbett diagram. And the blue diamonds are the position of the neutron star ULXs in this diagram, and there are several ULXs occupy the same region with B-type high mass-accretion binaries, like this. So it is easy to speculate that some neutron star ULXs are closely related to B-type high mass-accretion binaries. And it is known that B-type high mass-accretion binaries occupies the largest population among all high mass-accretion binaries. They are about 80% of all high mass-accretion binaries. So if B-high mass-accretion binaries universally become ULXs, that is, if B-high mass-accretion binaries produce super Eddington luminosity X-ray bursts, the possibility arises that a significant number of neutron star ULXs exist in the universe, because B-type high mass-accretion binaries occupies a large fraction of all compact objects. Hence, the question arises, what conditions must be satisfied for B-type high mass-accretion binaries to produce the super Eddington burst? So next, we would like to consider the condition to produce a large burst exceeding Eddington luminosity for B-type high mass-accretion binaries. Well, for a neutron star accreting from a B star to achieve Eddington luminosity, roughly speaking, two conditions must be satisfied. First, the mass transfer rate from the circumstellar disk of the B-type donor to the vicinity of the neutron star must exceed the Eddington rate. Furthermore, the mass transfer to vicinity of the neutron star must be accreted to the neutron star actually at a accretion rate greater than Eddington rate. As a first condition, we can apply the condition proposed by Okazaki-san in his previous study in this work, in which giant bursts occur in B-type high mass-accretion binary. The second condition is that the neutron star magnetic field must capture the accreting materials before the matter is blown away due to the disk wind around the neutron star. So next, we separately consider these two conditions. Well, in the previous work given by Okazaki-san, they examined the conditions under which B-type high mass-accretion binary can produce super Eddington giant bursts. In their study, they argued that the system is more likely to produce large bursts when the circumstellar disk around the BE donor is warped. And they also consider Bondi hole Richardson type accretion with constant relative velocity when a neutron star goes through the B circumstellar disk. In this case, the neutron star can capture a huge amount of materials from the circumstellar disk if the disk is warped, like this. And here we also consider such a mass capture process. And about this condition, we consider the mass transfer rate from the B circumstellar disk to the vicinity of the neutron star. For the circumstellar disk to be warped around the B donor, the tidal force must play a strong role inside the radius of disk truncation radius. The radius at which the disk is truncated and the radius at which the warping occurs due to tidal force are taken from previous studies. In these studies, and the condition can be described like this. This is the truncation radius of the circumstellar disk, and this is the warping radius of the B disk. And if the warping radius is smaller than the truncation radius, the circumstellar disk can be warped. However, this condition, this equation includes the viscosity coefficient of this circumstellar disk material in the vertical direction. And this factor is highly indeterminate. So we have to take care of the treatment of this value. I will discuss this point later. And then we consider the mass transfer rate from the BE disk to the vicinity of the neutron star by applying the normal Bondi-Hoyle-Littleton type accretion scenario. Here, the density profile of the BE circumstellar disk is assumed to be the standard model like this. And the material in the BE disk is assumed to rotate in the Keplerian manner. And the inclination angle between the disk surface and the neutron star orbital plane is taken as a parameter delta here. And this parameter affects the relative velocity of the neutron star and the disk material. From these assumptions, we estimate the mass transfer rate from the B disk to the neutron star vicinity. And if this mass transfer rate achieves the Eddington rate, the first condition has been cleared. Then the next step is to consider whether matter transferred from the B disk to the vicinity of the neutron star can actually accrete onto the neutron star or not. Well, transferred matter with a large transfer rate forms an accretion disk around the neutron star, like this. And however, because of the high radiation pressure, the accreted material, some of accreted material will be blown away by the disk wind inside a certain radius. The mass loss rate is determined by the ratio of the radius at which the radiation pressure is dominant and to the radius at which the neutron star magnetic pressure is dominant. This is shown by this factor. So taking into account the mass loss due to this disk outflow, the final mass accretion rate onto the neutron star can be computed by using this expression of each radii. And if the mass accretion rate achieves the Eddington rate, actually, the second condition to be second condition that neutron star high mass X-ray binary can produce super Eddington burst can be cleared. So I'd like to show the result next. This diagram shows such systems that satisfy these conditions. In this diagram, the horizontal axis is the orbital period of the binary system, and the vertical axis is the orbital eccentricity. When the donor and B disk parameters are taken as the standard values, this is shown here, and in this diagram, the colored area here is the region where the mass accretion rate can achieve the Eddington rate. The color contours represent the mass accretion rate, and with the yellow area being around 30 times the Eddington rate. And the three curves, this one and this one and this one, these three curves show the conditions under which the B disk is warped. The area under these curves, is the region where the B disk satisfies the warp condition. However, as I said, this warping condition depends on the viscosity of the B disk, and the actual viscous parameter is unknown. So this condition, we have to be careful about this condition. And after all, if we choose the central line, we can say that binary systems in this region can be a ULX, can produce super Eddington bursts. However, again, it is not clear which viscous parameter is appropriate. So it is very difficult to upper limit of this region. Well, in the case of high mass-accretion binaries, there are examples of huge bursts occurring even in systems with high orbital eccentricities like 0.5 or 0.6. So it may be better to choose a smaller value of viscous parameter alpha, like 0.5 or something, probably. And the obtained ULX regions varies according to the parameters of the donor. Especially the radius of the donor plays important role. Well, B-type star evolves relatively quickly and its radius increases gradually. As the radius of the donor increases from here to here, the circumstellar disk also increases. Then, large accretion rates can be achieved even in systems with long orbital period. As a result, the ULX region is extended from this one to this one. However, the luminosity of the burst itself does not change significantly. So, ULX conditions changes with the evolution of donors and also the evolution of binary systems. Especially the radius of the BE donor is important. So next we investigate how long a system can be a ULX during the binary evolution. Here we use the binary evolution code incorporates the determination of the ULX condition introduced earlier. The binary evolutions are computed from the birth of the neutron star, and the ULX conditions is checked at each stage of the evolution processes. And in this study, we use a binary evolution code constructed in my previous work with the aim of follow the evolution of the magnetic field and spin evolution of the neutron star simultaneously in binary systems. Well, in this work. And for the evolution of the binary systems as initial conditions for the calculation, a B-type star of age with 5 mega year is taken as the donor, and various binary parameters are given to start the computation. The computation is stopped when the donor evolves to fulfill its Roche law or to generate a supernova explosion. And computations are performed with different binary and B-disk parameters to investigate the period when the ULX condition is satisfied. And the results are shown in this diagram. As the same as in the previous figures, the orbital period and the orbital eccentricity plane is used here. And the duration of time of the ULX is shown as color contour. That is, in this binaries in this red region can produce super Eddington burst for about 10 mega years during its evolution processes. And the orbital period and the eccentricity change during the binary evolution. So in this diagram, we show the initial values of orbital eccentricity and orbital period are shown. And warp conditions also changes with the donor evolution. So I choose a relatively small viscosity coefficient and show two typical warping conditions at the initial donor condition and the final stage of donor evolution. And all observed BE-type high mass XL binary systems have a orbital period of more than 10 days. So we indicate this limit, observational limit, by this blue vertical line here. And the contoured area surrounded by these lines, this line and this line and this line, are the regions that BeHMXB binaries could produce super Eddington burst within its evolutionary process. It can be seen that for a significant part of the area, the period of time of ULX becomes the order of 1 mega year. As the lifetime of HMXB binary is around 10 mega years, so this burst duration 1 mega year is not very short. It's enough long to be observed. And then we would like to compare our result with observed high mass XL binary systems. The area indicated by the color contours in the last figure is indicated by violet lines, this line and this line. Between these two lines, the systems can produce super Eddington bursts for about 1 million years. And the remained warped condition is corresponding to the final stage of the donor evolution. And this region bounded by this curve and this curve and this curve and this curve. The bounded area by these four curves, this region, is the area where a binary system can produce super Eddington bursts at a certain stage of the binary evolution. And also, B-type BeHMXB binaries observed in the vicinity of our galaxy are indicated by blue circles in this diagram, like this one, this one, this one, and this one, and so on. This shows that a significant fraction of observed B-type BeHMXB binaries have the potential to become ULXs during some stage of their evolution. A certain fraction of these observed systems enters these ULX regions, I mean. On the other hand, the observed ULXs with B-type donors are shown by red stars. At first glance, these sources appear to be outside the X-ray ULX region. However, a slight change in the disk parameters changes the situation completely, like this. Well, under the same conditions as before, the results are shown in this figure. Only for the base density of the B circumstellar disk increased by a factor of 10. As can be seen, the result strongly depends on the disk density, and the observed ULX systems are well inside the region of ULX when the density is increased by 1 order of magnitude. This may indicate that the disk density is for some reason higher, triggering the super Eddington burst in B-type BeHMXB binaries. If there is a situation during the evolution of binary systems where the disk density increases a little bit, then a significant number of B-type BeHMXB binaries may produce super Eddington bursts and become observed as ULXs. Also, the inclination angle between the disk and BE disk and orbital plane has a similar effect. That is, it is also shown that when the disk plane are aligned to the orbital plane, the ULX region could become considerably wider, and a lot of systems can enter the ULX region. Okay. Through the binary evolution computation, we have shown that huge fraction of B-type BeHMXB binaries could potentially produce super Eddington bursts during their evolution. As the next step, we are preparing population synthesis simulation to reveal the actual fraction of ULX powered by neutron stars, not black holes. And also, we are interested in the classification of ULXs. Just same as BeHMXB binaries have two classes, supergiant systems and B-type systems, neutron star ULX may have several subclasses. We are trying to check any differences can be observed for the different types of ULXs. These informations could be a hint to tackle with the remaining problems on the neutron star ULXs that discussed in the introduction. Okay, so this is the last slide of this presentation. Here is a conclusion, but it's very short. Well, we have discussed that under certain conditions, neutron stars fed from the circumstellar disk could exceed the Eddington luminosity, and can be observed as ULX. And some fraction of B-type hemosexual binaries will evolve to ULX. And its lifetime is enough long, so they will be observed as ULX in future. And as a future work, we are preparing population census computations and try to reveal the real fraction of neutron star ULXs among all ULXs. Okay, I'll show the references of this presentation. Okay, that's all of my presentations. Thank you for listening, and I stop here. Thank you very much.
Thank you, Shige, for a very excellent talk on this interesting topic. Okay, Doug, please go ahead. Doug, guys?
Hi, Shige. Thank you very much. This was a wonderful talk. Could you
Thank you.
explain about, just remind me what you meant by small inclination? Was this between the warp and the magnetic axis? I didn't quite understand that point.
Well, just a moment.
It was that one point on page 29, on slide 29.
Slide 29, this one?
Yeah. Yeah, that, what did you mean by that small inclination? I had the same question.
Okay, well, the inclination angle between the circumstellar disk around the B stars and orbital plane affects the relative velocity between the neutron star and the accreting material in this form. This is the inclination angle. So when the inclination angle is smaller, the movement of the neutron star is aligned to the motion of the disk material. So the relative velocity could become smaller. And in this case, in the Bondi-Hoyle-Richardson type accretion, the accretion rate or mass capture rate could be larger. So in this meaning, when the inclination angle is smaller, the accretion rate gets higher, and the probability of the super Eddington burst can increase, I mean.
Okay, and then Matthew, please.
本当に面白かった、カリノさん。ありがとういたしまして。So a couple of questions. So you showed a large number of, I presume, galactic HMXBs that are sort of in the right part of eccentricity period parameter space. But as far as I know, we don't have any ULXs in the galaxy. So did you estimate the probability that we should see at least one given the population?
Sorry, could you repeat the question? I couldn't
do you have an estimate of the probability that we should see at least one galactic ULX?
Well, just a moment. Well,
I may have missed it, but
so now at least one ULX in our galaxy, but such kind of ULXs, neutron star ULXs with B donor behave as transient source. So it is very difficult to timely observe because how can I say, I forgot the word. Well, the duty cycle is unknown, and probably the duty cycle is very low, so it is very difficult to catch
Okay.
the giant burst. So it is important to increase the duty cycle of the observation. So in future, such kind of object will be found more and more, but at the present, it is difficult to the actual fraction, actual existing rate per galaxy. It's difficult to estimate. I'm sorry.
Okay, that's fine. Thank you for answering the question. I have one more, if that's okay.
Mm-hmm.
Is there expected to be any relationship between metallicity and the alpha parameter in the disk?
Metallicity. Okay, well, because the lifetime of high mass X-ray binaries are quite short, and so such kind of high mass X-ray binaries are only found in star-forming galaxies. So in such galaxies, the metallicity is just increasing. So in this meaning, the metallicity is related to the fraction of such kind of ULXs, I think.
Okay, thank you.
Okay, so we have one more people who wants a question or comment. Konstantinos, please.
I can't hear you, Constantino. Is it just me?
I just hear him, but it's extremely quiet.
Can you hear me now?
Yeah.
Yeah. Sorry. So hello. This is very interesting.
Thank
I'm
you.
actually a guest. I'm from University of Geneva, working on ULX population synthesis, which I see it's your next step. I wanted to ask you about, you mentioned the duty cycles, and this is very important because what I worry for lifetimes of the scale of mega years is, in order to have super Eddington accretion, you need such high accretion rates that possibly there is not enough material on the disk. If you account for 10 to the -7 or -6 solar masses per year, and for 10 mega years, you end up having disk material of the order of 1 solar mass. I don't know about the stars. I don't know if this is something that is expected, but it seems kind of too much. So the duty cycle is going to be important to understand if there is this material in the first place to accrete it.
Yeah, that is critical question. I'm afraid such kind of question. Well, in this study, we have only considered about the accretion or mass capture rate. This is only the rate. So we haven't considered about the total amount of captured mass, or total accreted mass. So this is just a rate. So it is necessary to supply enough mass to the circumstellar disk, and it should be kept in the disk for several orbital period and so on. But we haven't considered such kind of mass accumulation at all. So we have, frankly speaking, we have to consider about such kind of problem. So I've said that this is critical question for this presentation. Thank you for pointing out.
May
One
I
last
comment?
question.
Okay, go ahead.
Thank you very much. So you had two criteria that you have to transfer mass at super Eddington rates. And then you mentioned that you have to accrete onto the neutron star also at super Eddington rates. This is something that troubles me because the picture I have from the Sakura-Sunyaev model, or even the newer models from Bhutan, where they consider more realistic approaches to the accretion gas, the Eddington rate at the spherization radius, the transfer rate at the spherization radius is either equal to the Eddington rate for Sakura-Sunyaev, or even less in the Bhutan models, because supposedly the outflow is starting even further away throughout the whole disk. So you don't really have to accrete the material onto the cobalt object, and actually this is helping the explanation of having very high mass transfer rates, very luminous sources, or even beamed sources. So maybe I missed this part, but why do you consider that it should accrete at super Eddington?
Well, first of all, as you said, the Sakura-Sunyaev type disk, standard disk model can be used under the Eddington rate. So in this case, in such kind of super Eddington accretion case, the disk configuration is completely different. It should be the so-called slim disk type, I think. But about this problem, Okazaki-san will be will be expert of this type of problem. But, well, anyways, the disk model is different from the standard one. Does it make sense?
Oh yeah, the disk will be of the slim type, slim disk for the super Eddington luminosity, not the Sakura-Sunyaev type. Yeah, it will be thick in the vertical direction.
So we're talking more like Polish donut kind of thing.
And may I comment on the first point on the mass accumulation? Yeah, these systems, B-type X-ray binary systems, are transient, not persistent systems. So total mass accumulated on the neutron star should be small, much smaller than the, stellar mass. And also, circumstellar disk is replenished constantly. So yeah, it can support, rare giant outbursts. So there will be no problem with the mass accumulation in these transient systems, I think.
Thank you for the comment.
Much.
Okay. Oh, and I have one more question. Okay. Yeah, in the first, one of the first slides, you showed that there are many systems for which pulsations were not found, right? And you derive that they are the strong magnetic field systems, but usually X-ray binary systems have neutron stars with strong magnetic field of the type of the order of 10 to the 12 Gauss, and they are pulsating systems also in X-rays. So I don't get the point why no pulsation means a strong magnetic field.
Okay. Well, first of all, if the magnetic axis is misaligned from the line of sight, it is difficult to observe the pulsation. So fundamentally, we may miss a lot of systems, a lot of neutron star powered systems. However, from the spectrum of the X-ray observation, in some systems, actually in one system, we have observed a cyclotron resonance scattering feature that is caused by strong magnetic field around the accreting material. So in this case, as we know, if the central object is a black hole, such kind of strong magnetic field cannot be produced. So because of the existence of such kind of strong magnetic field, it means directly that the central object should be neutron starred. In this meaning, I have mentioned about the non-pulsating ULX. Among the non-pulsating ULXs, some of them may be neutron star powered one.
Okay, thank you. Are there any other questions or comments? No?
It was a very nice, interesting talk. Thank you.
Thank you very much.
Okay. So Carol, do you have any announcement?
Well, we'll have our next talk in always on the third Wednesday of the month, and certainly we'll be advertising again in the Massive Star newsletter and on the BE's Disc website. And if anybody wants a regular notification, just send an email to my PhD student, Mark Suffix, who sends out another reminder as well with details about the next talk. And he also put in the chat the link to the previous talks that we've been recording. So if you've missed one and want to watch one, just go to the link and see it. And also, just so you know, that the Atsuo, Dietrich Bode, myself, and Alex Cardovi and Greg Wade are all part of a committee where we select and invite our speakers for the forum. And I'm sure that any one of us would be happy to get suggestions for some of the talk. We try to give especially the early career researchers a chance to present their work when we haven't been able to travel as much in the last couple of years. But you know, there's lots of interesting things out there, and sometimes it's hard to know what we should bring to you. But if people have suggestions, feel free to submit them to any one of us. We'd be delighted to get your suggestions. And thank you very much, Atsuo, for hosting this one and inviting the speaker and looking after the questions. I appreciate that. Thank you, everyone, for coming.
Okay. Thank you all. Thank you, Shige, particularly.
Okay, thank you very much.
Mm-hmm.